This is the last conversation I want to have with you all when it comes to the introductory week on functions. I'm going to do a lesson here with 3 examples, and then for our last video of the week, I'm going to pull a couple of examples from homework and do them through. So what I want to talk to you about here is graphing piecewise defined functions. And again, like I said, this will be the first of 2 videos on that topic. I want to start with the big idea. So the idea is that, as you remember, a piecewise defined function has a different rule that it applies to different pieces of the domain. So the first thing that I like to teach about graphing piecewise defined functions is to identify the pieces on the x-axis. So you remember that for our purposes, the inputs live in the x-coordinate, which means that the x-coordinate is where the pieces of the domain are going to change. So that's the first thing we're going to do, and you'll see what I mean in the example, that we first piece out the domain. Second, plot the points, and then I call it at the seams. So what do I mean by that? I mean, like I said, a piecewise defined function is made up of pieces. So you're going to have places where one piece ends and places where another piece begins. And so it's important to plot those seam points, the points where the one piece stops and the other piece begins. So I always like to start there after we've identified the pieces on the x-axis. And then the last step is not very, there's not a lot to say here, but I'll say here, plot more points as needed. And the reason that I'm saying this is that depending on the types of rules in your pieces, if you're looking at a constant function, you really don't need anything except for the seam points. If you're looking at linear functions, you need one other point except for the seam point. And then in the next lesson that I'll show you, we'll look at a quadratic function where you might need 2 or 3 points. So it depends on the type of piece, how many points you're going to need per piece. So we'll kind of play with that and look at some examples. So in our first example, we're being asked to graph this function. F of x is -1 if x is less than 2 and 3 if x is greater than 2. I'm not going to write the flowchart out, but if we were to write the flowchart, the way that this works is if you're giving this function an input less than 2, it outputs -1. Regardless of what that input is, if the input is less than 2, the output is -1. If the input is bigger than 2, regardless of what it is, the function outputs 3. Notice, so I'm just going to say this here, that we have a rule defined for inputs less than 2 and for inputs greater than 2, but we do not have a rule defined for the input 2 itself. We'll talk more about that in a second. All right, so remember how I said identify the pieces on the x-axis? So I'm going to actually do that in red. Everything breaks at 2. You have one rule leading up to 2, so that's going to be sort of piece 1. And then you have another rule after 2, so that's piece 2. So now we've identified the pieces. It doesn't take very long, and we look here to see where our pieces are. All right, now plot the point at the seams. So if x is less than 2, so that's piece 1, the output is -1. So you know what I'm going to do? I'm actually going to erase this 2 here to make a little bit of room. For any input less than 2, so for anywhere leading up to here, the function outputs -1. So here's what I'm going to do. This is -1 here. Now watch. Because it's strictly less than 2, I'm going to put an empty dot at the point 2, -1 to indicate that at 2, this function does not assign the output -1, but all the way up to 2, it assigns the output -1. So that is the first piece. Now let's look at the other piece. So what happens at the seam? Well, f of x is 3 for any value of x greater than 2. So any value here, any value greater than 2, the output that this function assigns is 3. Not 2 itself, though. So I once again put an empty circle there. And then anywhere greater than 2, the output is 3. A little empty spot here. Let me fill that in. So that is the graph of this function. Now, we're going to come back to this at the end of this lesson because I actually want to use our lesson right before this one to talk about the domain and the range of this function now that we've seen the graph. But I want to move on and I want to do a couple more graphing examples first. Example 2. So again, let's look here. So the two pieces are if x is less than or equal to 2 and if x is greater than 2. So again, the seam happens at 2. So I'm just going to identify that. This right there is where the function switches from doing one thing to doing another. Now, let's plot the point at the seam. The top piece is x plus 3. 2 plus 3 is 5. 1, 2, 3, 4, 5. Now see how here it says if x is less than or equal to 2. So that actually means that at 2, this function behaves like x plus 3. So to indicate that, we put a filled in point at 2, 5. Now, for any input that's greater than 2, strictly greater than 2, not equal to 2, the function behaves like 1 minus 2x. If we plug 2 into 1 minus 2x, we get 1 minus 4, which is -3. And again, that's not how this function behaves at 2, only greater than 2. So we indicate that this point is not on the graph by an empty circle. Now look, both of these pieces are linear. So linear equations, the reason that they're called linear is in particular because their graph is a line. You only need 2 points to graph a line. So over here, when I say plot more points as needed, I only need 1 more point for each piece. So for the top piece, let's pick another value less than or equal to 2, like 0. If x is 0, x plus 3 is 3. And so then, if I connect these dots, there is that line. So that is the top piece. Now, 1 minus 2x, same thing, that's linear, so I only need one other piece. If x is 3, I have 1 minus 6, which is -5. Okay, so it goes through that point. And I can connect these two dots. And I get something like this. So that is the second piece. So that's the graph of this function. Okay, notice that I put little arrows on the edges of my pieces to make it really clear that both of these go on forever. We do not have a stopping point. All right, for example 3. So example 3 is a little bit interesting because it says here that this function does one thing if x is less than or equal to 0. And another thing if x is strictly greater than 1. So the pieces don't butt up to each other. One of them ends at 0 and the other one starts at 1. So there's a gap between 0 and 1. So when I go to delineate my pieces, here is one of them and here is the other. So like I just said, there's going to be an empty space between 0 and 1. All right, let's do the seams. So what do I mean by that? What I'm asking you for here is I'm asking you for the point where the one piece ends and the other piece begins. In this case, there will be two of them because the pieces do not butt up to each other, and so the pieces don't meet. Okay, 2 minus x. If I plug 0 into that, I get 2. And notice it says here if x is less than or equal to 0. So the point 2, 0 is actually going to be filled in on my graph. I misspoke. I said 2, 0. I should have said 0, 2. For 1, notice that this is a strict inequality. It's x plus 5 if x is greater than 1. If I plug 1 into x plus 5, I get 6. So that's up here. But again, I need to make this point, let me actually make that a little neater. I need to make this point empty because that inequality is strict. So those are my 2 points at the seams. Now we're in the plot more points as needed category. So for the top piece, 2 minus x, notice that again, both of these are linear. So I only need 2 points to graph them. So I need one other point from the top piece. I don't know, let's try -1. If x is -1, 2 minus x is 3. So now let's connect these 2 points. And there is that top piece. Okay. And then same thing for x plus 5. That's a linear piece. So I only need one more. So I mean, let's try like x equals 2. If x is 2, x plus 5 is 7. And once again, here is my second piece. Oops. Okay, so now that I've graphed these two, let's go back and talk about domain and range. So this is an excellent opportunity for us to revisit the conversation from our last lesson. So remember, domain is the set of possible inputs. So when we're using the graph to talk about domain, what we're doing is we're tracing along the x-axis to see if there are any points that don't any values on the x-axis that don't correspond to a point on the graph. So what do you think? As I'm tracing along, everything is fine until I get to 2. And you can see that when x is 2, the only 2 points that seem like maybe they would work are actually both blank. So neither one of them is actually part of the graph. And then I keep going and everything is fine. So I have a blip at 2, and then all other real numbers appear to be included. So my domain is all real numbers except for 2. Right, and if you wanted to write that in interval notation, you could also write it like so. So making sure that you are skipping the 2 as you go from negative infinity to positive infinity. The range here is interesting, right? Because the range consists of all of the possible outputs, and this function doesn't have much in the way of possible outputs. Any input you give it, except for 2, it either gives you back -1 or 3. So if we do our tried and true method of tracing along the y-axis, you can see nothing doing, no point with these y-coordinates. Oh, here there's lots of points with that y-coordinate, so -1 is part of the range. Then nothing. Oh, lots of points with y-coordinate 3, so 3 is part of the range. Nothing. So there's only 2 values along the entire y-axis that are part of the range. So to indicate this, we can actually use curly brackets, which are handy in situations when you have an actual finite list and you want to enumerate some numbers. So that's not an interval. The range is not all real numbers between -1 and 3. it's only the numbers -1 and 3. Okay, now let's look at the second example here. So the second example is actually going to go really quickly. So tried and true, let's trace along the x-axis. There's points here, there's points here, there's a point at 2, and there are points everywhere to the right of 2. So it turns out the domain here is all real numbers. Okay, so then we look at the range. Okay, so what do we have? So we're tracing along the y-axis. Yep, there's a point, there's a point, there's a point. Now here you might be tempted to say, wait a minute, there's a blank point to the right, so does that mean we have to skip -3? Nope, because even though there's a blank point to the right, there's a perfectly happy point to the left. So nothing to skip there. Moving along, moving along, moving along, moving along. Everything is fine. Oh, this is the end. So everything was fine up until we got here, but then there's nothing doing after 5. So the range is all real numbers up to and including the 5, because there actually is a point on this graph whose y-coordinate is 5. So the range is all real numbers up to and including 5. Last example, domain and range. Tried and true, let's trace along. So as we're tracing along the x-axis, there are points with these x-coordinates. They're above the x-axis here. Everything is good, everything is good. We're good all the way until 0. Then there's a blank spot. There's nothing happening between 0 and 1. It starts up again right after 1, but not including the 1 itself. So the domain skips everything between 0 and 1, and this is how we would write it in interval notation. The domain is everything up to and including the 0, and then it starts again. Let me make that more clear. It starts again at 1, but not including the 1 itself, and then goes on to infinity from there. Now let's think about the range. So same thing, right? We trace along the y-axis, but look, there's nothing here. As you are moving up the y-axis down here, there are no points with those y-coordinates. The graph hasn't started happening yet. Oh, this is where it starts. So the range starts at 2. And then from there, it actually doesn't have any more problems. Again, you might be tempted to think, wait a minute, there's an empty point there, so maybe I should exclude that. But even there's an empty point on the right, there's a perfectly happy point on the left, so we don't need to skip that point there at 6. And so you keep on going, everything is fine. And so the range starts at 2 and then goes to infinity from there. So that is the range of this function. So I hope that this gave you an overview of how graphing piecewise defined functions works. And in our final lesson for the week, I'm just going to pull 1 or 2 problems from homework having to do with graphing piecewise defined functions so that we get a chance to do one more example. And then we'll be done for the week. Thanks for your attention. Bye.